So how do we evaluate a definite integral? Well, we're going to use the fundamental theorem of calculus in order to do that. Now, we've talked about in the very first section the antiderivative. And remember, when you do this, if you can evaluate this derivative, you get a new function plus c. You get a family of functions. Now, the definite integral, when you evaluate it, you get a number, not a family of functions, a particular number. So this can be used to find area, for example. This can only be used to find the antiderivative of the function. So here is the fundamental theorem of calculus. Now, some books, they call this the first fundamental theorem. Some books, they call it the second fundamental theorem. Our book just calls it the fundamental theorem. It says that if you have a continuous function on a closed interval, and f is the antiderivative, back from section 1, on the interval, then the definite integral from a to b of fx dx is the value of the antiderivative at the top index minus the value of the antiderivative at the bottom index. And so if we want to find the value, and we want to use the fundamental theorem of calculus, you have to be able to find the antiderivative of the function. And we know ways to evaluate that without using the limit, right? So we don't want to use the limit definition. We're going to use the rules, the formulas. When applying the fundamental theorem of calculus, the notation is how you do it. The integral of the function dx from a to b is equal to the antiderivative of f, and we're going to evaluate it from a to b. So we put in the value of b into the function, get a number, put the value of a into it, get a number, and subtract them. For example, the integral from 1 to 3 of x cubed dx. Always have to have that dx there. Well, we talked earlier that we can do the antiderivative of this. It's x to the 4th over 4, power rule, from 3 to 1. So we put 3 in, 3 to the 4th over 4, minus 1 in, 1 to the 4th over 4. So 81 fourth minus 1 fourth equals 20. And we have evaluated the definite integral. Now, remember, when you did the antiderivative, you got the function plus c. And when you evaluate from b to a, that becomes the value of the function at b plus c, and the value of the function at a plus c, subtracting those, and the c's go away. So when we are doing a definite integral, it's not necessary to include the constant. When we are doing an indefinite integral, we must have that constant there. It's part of the answer. That's part of the answer. Oh, okay, let's try to use it. Here's a function. X squared minus 3 dx from 1 to 3. Definite integral. Means if there's an answer, the answer is a number. Well, the integrals of differences are the integral of each piece. So the integral of x squared, the antiderivative of x squared is x cubed over 3. The antiderivative of 3 is 3x from 2 to 1. So we put 2 in. 2 cubed, that's 8. So 8 thirds. 3 times 2 is 6. So 8 thirds minus 6. And we put 1 in. 1 third minus 3. And then we subtract those two values. In this case, we get minus 2 thirds. That is the answer to the definite integral. The integral from 1 to 4 of 3, the square root of x dx. Well, first, with this constant, we can move it to the front. The integral from 1 to 4, and we don't have a square root rule, so we have to rewrite it. Rewrites the key, x to the 1/2 dx. So x to the 1/2 dx, power rule, add 1 to the power. 1/2 plus 1 is 3/2. And then divide by that 3/2. So we have 3x to the 3/2 divided by 3/2 from 1 to 4. So when you're dividing here, this means the 2 goes up to the numerator, 3's cancel, 2, 4 to the 3/2 minus 2, 1 to the 3/2. Square root of 4 is 2. 2 cubed is 8, so that's 16. 1 to any power is 1, so 16 minus 2 is 14. And there is your result. The integral from 0 to pi over 4 of the secant squared of x dx. Definite integral. Can I do this and find the antiderivative? The antiderivative of that is tangent, because the derivative of the tangent is secant squared, so the integral of the secant squared is tangent. From 0 to pi over 4. So the tangent of pi over 4 minus the tangent of 0. Tangent of pi over 4 is 1. Tangent of 0 is 0, until we get 1. Okay? That is how you do. I'll do a couple of pin casts on these other examples, but I want you to see that's how you use the derivative. Okay? It's how you use the derivative. Couple of pieces that are just formulas so that you use the definite integral. Mean value theorem. Continuous function on a closed interval, then there exists some number c in the closed interval for which the definite integral is equal to f of c b minus a. So it's a formula. So if I want to find c, I have a and b, so I know this. I know what the function is because I'm given it. And I've got an antiderivative, definite integral. So if I can figure out the antiderivative of f, I can figure out what this number is. And if I know that number, I can evaluate for c. And that's the mean value theorem. Another theorem that makes you use a definite integral. These are just theorems that make you use definite integrals. Okay? The average value theorem. It says that if you have a function and it's integrable, so here's our function. From a to b, so it's on a closed interval from a to b. Then the average value, the average y value. See all these y values? If you could add them all up and divide by the number, but you can't do that because there's an infinite number of them. But that's how you find the average. You add up all the quantities and divide by the total numbers. Well, we can't do that because of the infinite values there. But integrals help me take limits of infinite values. And so the average y value is 1 over b minus a. You know a and b, so you plug them in. The definite integral from a to b of f of x dx. If you can evaluate this number, you now have the average y value. The average y value. So just formulas using that. Right? Here's a great example. Go back into the book and look at it. We're told that the speed of sound travels at, and we are given a number. But that number is an average value, really, because here's really what the graph is. At different heights, the speed of sound changes. And here is what it happens from 0 to 11.5 meters up. That formula gives you the speed of sound. And you see the rest of them. And so if we take each of those integrals, okay, the integral of the function, minus 4 plus 341 dx from 0 to 11.5, we have a number. And if we find the next number, and we find the next number, and by adding up those 5 values, you get 24,640. And so the average speed, because we have, in this case, we're going from 0 to 80. So 0 to 80 gives about 308 meters, okay? That's usually the kind of approximation we give. But in reality, it's a cool example. Spend some time looking at it. Check it out. See what you think. Right? Now, there is a second fundamental theorem. Again, some books call it the first. Okay? So if you have from a to b of f of x dx, a and b are constants, here's the function. Right? And it equals a number. It equals a number. Okay? The definite integral of a function says this. You have f of x dx, but now we're going to change it to t because we're going to function t. Remember, variables are dummy variables. So instead of x, we're going to put t, f of t dt. So this integral and this integral are exactly the same antiderivative, except this will be an x and this will be in t. You'll put in a and b and get a number. Here, you'll put in a and x and you'll get a function. For instance, the integral from 0 to x of the cotangent of t dt. Right? Well, the integral of the cotangent is secant. Is sine. Derivative of sine is cosine, so the integral of cosine is sine. From 0 to x gives me the sine of x minus sine of 0, which gives me the sine of x. And so this function, this definite integral as a function, turns out to be s of x, which leads to the second fundamental theorem of calculus. It says that if you have that particular function, the integral of f of t dt from a to x, and you take the integral, you can figure it out. If you now take the derivative of that, it'll give you f of x. It'll give you f of x. That's what the theorem says. It's not real earth-shattering, but it's very important in some other applications. It's very important in some other applications. The integral from 0 to x of the square root of t squared plus 1 dt. Now, we don't have the tools to do that integral yet. We will later, but we can't do that integral yet. But because this is going to be a function, the second fundamental theorem of calculus tells me that the derivative of that is just the square root of x squared plus 1. It's the derivative of the function evaluated at x. And the second fundamental theorem of calculus. The second fundamental theorem of calculus. There's a few other examples in the chapter. Spend some time looking at them. Here's one as an application. We already know that the velocity, a function, right, in feet can be moving along this function. So a function like this, moving along. So this is going along that function. What is the displacement of the particle from 1 to 5? Well, that's the definite integral from 1 to 5 of that function. I can do t cubed, t to the 4th over 4. I can do t squared, t cubed over 3. 10 is along for the ride. I can do t, that's t squared over 2. And I can do a constant. Evaluate it from 1 to 3, and you get 32 thirds. So the particle moves 32 thirds, or about 10 2/3 feet to the right. Okay? But that doesn't mean that is what it covered, because it could be oscillating back and forth. To find the total distance, time the total distance, right? So here is the guy, right? It's displacement. But to find the total distance, we have to find the distance, we have to find the integral from 1 to 4, and then from 4 to 1, but this is going to be negative, so I need to take the opposite of it, and you'll find out that it actually traveled 71 divided by 6 feet. Okay? It was displaced about 10 feet. From where it started to where it ended was about 10 feet, but how far it traveled, right, was over 11 feet. So you check those out. So that is the fundamental theorems of calculus. Should be now able to do some definite integrals.